Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This course is Introductory Transport Phenomena, based on the book by Welty, Rohrer, and Foster. We are looking at Chapter 1, Introduction to Momentum Transfer, and in this video we'll be talking about fluids and the concept of a continuum. Okay, so in this first portion of the course, we're going to be talking about momentum transfer. And we're going to be looking at the behavior of fluids both at rest and in motion. So, of course, the first real question we should ask then is, what makes something be a fluid? Now, the simplest basic distinction is differentiating between a solid and a fluid, right? A solid will hold its shape, and a fluid flows to fit the shape of the container. So in the picture here, we have a solid ice cube, we have the liquid, which is a fluid, in the bottom of the glass, and in the space around it, we have air. Of course, this definition kind of bumps into a few problems. So for instance, think about toothpaste. It will flow out of a tube like a liquid, but it holds its shape, right? Once it's piled onto the toothbrush, it just sits there. We have things like glass or honey, jelly, tar. All of those things are examples that don't really easily fit into this simple definition. And these bizarre behaving substances are called non-Newtonian fluids. So what is a Newtonian fluid? Well, this is going to be one that deforms continuously when acted on by a shear stress. So for instance, stirring of any magnitude. Water, air, oil, all of these are Newtonian fluids. And the majority of this course is going to apply directly to Newtonian fluids. Non-Newtonian fluids are a little trickier and will require some special analysis. So what about non-Newtonian fluids? They're a little bit trickier because they fall into several different categories. Being in plastics resist small shear stresses indefinitely, but they flow easily with a large shear stress. Examples of this would be toothpaste, right? You squeeze the tube and it flows, but just little small shear stresses, they just stay kind of solid-like. Bread dough, jelly, those all fit into this category. Pseudoplastics, so these, their viscosity decreases with the velocity gradient. So the more you stir them, the less viscous they are. So mud, blood, polymer solutions tend to fall into this category. The last category is probably the most rare and the strangest. The viscosity actually increases with the velocity gradient. Starch suspensions are our most well-known example in this category. We've been casually throwing out these technical terms. We're going to begin formally defining these in the next lessons. But first, we need to think about how we are going to consider these fluids. Most of the time, we're going to think of the fluid as a continuum, but we have choices. So you can look at this on the molecular level, right? Every individual molecule has its own motion and its own properties, and they can be attracted or repelled by their neighbors, right? There's space between those molecules. Sometimes that's a useful point of view, but for this course, it's mostly going to be helpful to take a step back. And we want to do it just far enough back so that the space between the molecules blurs. Okay? In that case, we can do this on a microscopic level. Still looks like a continuous fluid. Okay? The molecules are going to act together as a continuum, and that can be very useful. But sometimes we're going to even want to step further out to the macroscopic level. This is going to be very useful because then the properties are going to vary smoothly, continuously from point to point. As we discuss things in this book, you're going to see that we're frequently going to go from the microscopic to the macroscopic level and use that to help describe the things that we observe about fluids. In our next lesson, we're going to be looking at properties that are very common and core to our study of momentum transfer. Thank you very much for your time, and if you have any questions, feel free to contact me.